So welcome. So in the previous video, we talked about heat transfer and different modes of heat transfer. We stated out the laws governing them, and then we gave our formulas for what analyzing or solving problems on each of those modes of heat transfer. So in this video, we're going to be talking about one-dimensional heat transfer through a single wall. Let's say we have a solid wall, just a single solid wall, okay, and let the distance or the thickness of this wall simply be x, simply be L. Let the thickness of this wall simply be L, and we have a heat being transferred through this wall, Q, of course, at a temperature T1, which is always a higher temperature, down to a temperature T2, which is the lower temperature. And of course, let the thermal conductivity of this wall, since it's a solid body, let the thermal conductivity simply be what? K. And I said heat transfer in solid bodies is always by conduction. So simply we'll have K to be the thermal conductivity of the body. Now, this heat is being transferred from this temperature T1. It loses temperature to temperature T2. Okay, it loses temperature to temperature T2. Now, the law that governs conduction heat transfer is simply Fourier's law, and that law simply states that Q is equal to, which is heat, is simply equal to, we obtain Ka, okay, and we simply said it is always T1 minus T2 all over X2 minus X1. So this is the heat transferred by conduction for a given wall which conducts a heat between two temperatures, just like we have in this case now. At this point, or at the beginning of the wall, X1 is actually equal to 0. Meanwhile, at the end of the wall, X2 is actually equal to total length, which is L. You have L. Therefore, we can have that X1, X2, we can have that X2 minus X1 is now equal to L minus 0, because X2 is L, X1 remains 0. So this simply implies that the X, which is X2 minus X1, is actually equal to L. So for a one-dimensional heat transfer through a solid plane wall, we are going to have that the heat transferred Q is actually equal to Ka times difference in temperature, the first temperature always minus the last temperature. So I'll simply have T1 minus T2 all over. X2 minus X1 gave us simply L. So simply all over L. So we have this. And of course, if I want to rewrite this equation now, I can simply have that Q is equal to, from board mass, this will be T1 minus T2 all over, this becomes L over Ka from board mass. So I can simply send Ka under here simply by board mass. Let's just explain that concept now. Normally, if I have 2 divided by 3 over 3 divide or over 4 divided by 5. If I have this from board mass, I'm having 2 divided by 3, I'm having 4 divided by 5, and I'm having this division sign. So 2 divided by 3 is actually dividing 4 divided by 5. If I want to change the division to multiplication, the law simply says it becomes 2 divided by 3. Changing the division now to multiplication, I have to now inverse, take this 5 up, it becomes 5 divided by 4. So what now happens if I have, okay, I'm taking this off now. So what now happens if I have 2 all over 3 all over 5? So I'm having 2 dividing 3 divided by 5. So which means these 2 dividing 3 divided by 5 can also be written as 2 all over 1. Okay, if I want to change this to division, this division sign now to multiplication, it becomes 2 times what? 5 comes up, 5 all over 3, which is still the same thing here. So from this place now, if I want to, I'm having T minus T2 all over L over Ka. So if I want to transpose this equation, it can also be written as what? T1 minus T2. Okay, I want to change this division sign to multiplication. It becomes times, then K over Ka goes up, it becomes times Ka all over L, which is still the same thing as what we had here, which is simply Ka times T1 minus T2 all over L. I will still have this same equation. Okay, so I'm taking this off now. So this equation can also be written simply as this. Q equals T1 minus T2 all over L over Ka, where this top represents what is called the temperature difference. Is called temperature difference. Okay, meanwhile, this is actually called the heat supplied or heat transferred. Okay, heat transferred. So if we compare this to electrical analogy, recall from Ohm's law, recall from Ohm's law, okay, from Ohm's law, we have that V is actually what? I R, and therefore we can make current subject of a formula, and we'll obtain I to simply be what? V all over R. And we call V simply what? Potential difference. We call V potential difference, and then we call I current transferred. Okay, we call I current transfer. So if you compare those two equations, you have Q for heat transferred, you have I for current transferred, you have T1 minus T2 for temperature difference, you have V for potential difference, and in electrical analogy, we call R simply what? Resistance, electrical resistance. We call R simply electrical resistance. Okay, so which means L over Ka can be likened to simply be called the thermal resistance. So we simply call L over Ka thermal resistance. If you compare it, so that is simply called electrical analogy of what? Heat transfer. T1 minus T2 stands for temperature difference, just like V stands for potential difference. I have I here, which stands for current transfer, just like Q stands for heat transferred. So if R in electricity is actually electrical resistance, it now means that L over Ka is actually called thermal resistance. So we can now rewrite this equation for heat transfer between a solid body as simply heat is equal to temperature difference T1 minus T2 all over thermal resistance RTH, where RTH itself, which is the thermal resistance, is simply what? L over conductivity times area. So we simply have this. Okay, now let's observe when we have more than one plane. For instance, let's say we have a composite wall, that is to say more than one wall, and then heat is being transferred at different temperatures. Let's observe that and see how it works. So let's consider when heat is transferred through a composite wall. So we simply have the first wall, and then we have another wall attached to it. Okay, up to two walls now, and then we have heat being transferred through this wall. Call this heat Q. Okay, and of course the first temperature here is temperature T1, and okay, this heat is being transferred from this wall to this wall at a temperature here, call this temperature T2, and finally to this wall at a temperature, call this temperature T3. Let the length of the first wall simply be LA, call this LA, and the length of the second wall simply be LB, call this LB. Okay, let the thermal conductivity here be Ka, and the thermal conductivity of this wall be simply Kb. So we have heat transfer between what? A composite section. So you could also have more than one section, like up to 3 or 4 different sections. That's why it's called a composite section. So I'm using these two composite sections to actually explain this term now. So just like in the first case, the heat transfer between temperature T1 and T2, okay, let's do that here. Heat transferred between, okay, T1 and T2, heat is actually equal to, so it is always the first temperature minus the last temperature. Take that in mind, or have that in mind always. Heat can always be transferred from the first temperature, difference between the first temperature and the last temperature. Okay, because the first temperature is always going to be higher than the last temperature. So if we're saying between T1 and T2, the heat transfer simply becomes, so the heat transfer between those two, Q, is now equal to, we said from Fourier's law that heat transferred Q is actually Ka into dt all over the x, or minus the T over the x, and we transpose that equation to become Ka into, now change in temperature becomes T1 minus T2 all over, now the length, of course, at this point x1 is equal to 0 and x2 here is equal to what? Simply L, and this difference simply give us what? LA. All right, so this is simply all over LA. Okay, so remember this is actually Ka, thermal conductivity of the first wall, which is this. So you simply have this equation. Now let's try and make temperature subject to the formula. All right, so from here, we also observed in the previous video that I said this equation can be transposed as simply T1 minus T2 all over LA divided by Ka times A, which is the area. So if we make temperature T1 minus T2 subject to the formula, we're simply going to have T1 minus T2 to now be equal to the whole of this value, L over Ka, multiplied by the heat. So I'll simply have Q into LA all over Ka times area. So simply call this equation 1. Now, we consider heat transfer between temperature T2 and temperature T3. Okay, so heat transfer, HT stands for heat transfer between T2 and T3. So always the first temperature minus the last temperature. So it's going to be T2 minus T3. And that heat is simply Q equals Kb, which is thermal conductivity of that particular wall, times the area into, it becomes T2 minus T3 all over Lb, which is the length of that particular wall. Okay, and of course, if we transpose this equation, it becomes T2 minus T3 all over, this becomes Lb divided by Kb times area. So again, let's make the temperature difference subject to the formula. So if we make T2 minus T3 subject, we are going to have that T2 minus T3 is actually the heat supply, which is Q, multiplying through by what? LB all over Kb times area A. So let's call this equation 2. In order to obtain the total heat transferred or total temperature, we simply would add equation 1 to equation 2. And if we add 1 to 2, adding 1 to 2, equation 1 and equation 2, we are simply going to have T1 minus T2 plus T2 minus T3, and that's simply equal to, we have here Q into LA, we simply have Q into LA all over KA times A, okay, plus Q into LB all over KB times A. So if we have this now, notice here now that we have T1 minus T2 plus T2 cancels out. So we simply have T1 minus T3, and that's simply equal to, of course, it's still the same intensity of heat that goes through the plane Q. So heat is the same. You can make Q subject into, it becomes LA all over KA times A plus LB all over KB times A. So you simply have this equation. So let's make heat subject of the formula now. If we make heat Q subject, it simply becomes T1 minus T3 all over, you simply have it to be LA over KA times A plus LB all over KB times A. So you have this equation, but not forgetting that we simply said in the previous video that L over Ka actually stands for what is called the thermal resistance. Okay, so which means this heat is actually equal to T1 minus T3 all over La over Ka times A, simply gives us RTHA, which is simply the thermal resistance of the first wall plus RTHB, which is simply the thermal resistance of the second wall. So two things to note here. First of all, when heat is transferred between, regardless of the amount of temperatures involved, heat transferred is always the very first temperature minus the last temperature, as can be seen from the equation. It became T1 minus T3, neglecting this temperature in between. So regardless of the amount of temperatures in between, heat transfer is always the first temperature minus the last temperature, always between these two. And then if this wall is simply a plain wall, because this heat transfer now is in series, the same intensity of heat coming here is still the same intensity of heat going here, even though it has undergone reduction, but it's still the same Q that flows through all of them. So if we have this plane to be in this manner, it means this plane is actually what? In series. So this is a series plane, and as such, all we need to do is to what? Add their thermal resistances, just like we do in electrical analogy. If we have resistors in series, we add. But if we have resistors in parallel, of course, we take the inverse of the resistors to obtain the equivalent. Okay, so but simply, if we have a composite wall section such as this, and of course, heat is being transferred, and this wall is not in parallel but in series, then the heat transferred is always the first temperature minus the last temperature divided by the sum of the thermal resistances. So in terms of electrical analogy, we can simply now put in, this is the first temperature, T1, and this is the wall. So I simply have this wall, and then now the heat is being moved, experiences a thermal reduction due to what? Conductivity. So there's a reduction by conduction. That reduction is what we call thermal resistance, which reduces the intensity of heat flowing through the wall. Okay, and then out to this other temperature T2. Now the heat is being transferred also from T2. Before getting to temperature T3, it also experiences another thermal resistance, okay, before getting to temperature T3. So you have this, where this is simply RTHA and this is simply RTHB. Okay, so this is thermal resistance at A and this is thermal resistance at B. So all you need to do is to what? Always represent your equations in terms of electrical analogy, and then since they are in series, you simply add up the resistance, take the difference in temperatures and divide by resistors. That gives you the heat transferred through the wall. Okay, so having known this now, we are going to try a different wall. Let's say we have up to three walls now. We'll try and see the heat transfer between these three walls by electrical analogy without going through these whole rigorous exercises. We can just get the answer in one step. Let's try it now and see. Okay, so let's say we have more than one plane now. We have this, about three planes now. Okay, and then we have heat flowing through the plane Q. Let the length of this plane simply be LA. Let the length of this plane simply be LB. Okay, call this LB, and let the length of this plane simply be LC. Okay, let heat be transferred from, okay, from the higher temperature is T1, heat transferred here down to this point. So let the heat transfer, the temperature here be T2, temperature here T3, and the final temperature be T4. So without going through those rigorous exercises, let the thermal conductivity here be Ka, conductivity here be Kb, and here be Kc. So it's simple. This is also a series wall. Since it's a series wall, you see apply electrical analogy to it. I have temperature T1 here, and I have okay, this is this side of the wall. Okay, this is temperature T1. Now this heat flows and experiences a thermal reduction or thermal resistance before getting to this temperature T2. The same thing happens, the heat flows from this temperature, experiences also a thermal resistance before getting to this temperature T3. And finally, this same heat flows through and experiences a thermal resistance before getting to temperature T4, which is the final temperature. So the thermal resistance here is simply called RTHA. Thermal resistance here is called RTHB, and here is called RTHC. You simply have this. So in general, we know that heat transfer Q, I always say, is the first temperature minus the last temperature. Regardless of the amount of temperatures in between, it is simply between the first T1 minus T4 all over. Since this wall is a series wall, the same heat intensity flows throughout. So you simply what? Add up their resistances. So you simply have RTHA plus RTHB plus RTHC. So simply what? T1 minus T4 all over the sum of the thermal resistance. That gives you the heat transfer through this wall. And of course, you know the values of the thermal resistances. Um, so that's simply saying heat is actually T1 minus T4 all over RTHA is simply given as LA all over Ka times the area plus also RTHB is simply given as LB all over KB times area plus RTHC, that's simply LC all over KC times the area. So this can also be written as this. So that becomes the heat transfer through that particular plane when they are in series. So if you have heat transfer between planes in series, that is how you're able to analyze them. So what happens when they are in parallel? Okay, so if we have planes in parallel, still the same thing, just like we do for resistors in series and in parallel. Once resistors are connected in series, we add their total resistance to obtain the equivalent resistors, just like we have here. But if they are in parallel, then there's always a need to take their inverse and obtain their equivalent resistors in parallel. In the next video, I'll talk about when the heat is being transferred through a parallel plane wall, and of course, also show you how to obtain the values of the equivalent resistors, okay, before we start solving problems on them. All right, guys, I will see you in the next video. Please, if you're new to the channel, don't forget to hit the subscribe button, to keep getting updates when more content on heat transfer drops. I will see you in the next video. Thanks.